Welcome to this lecture series in linear algebra. In this lecture, we'll look at matrices and their connection with linear maps. And let us recall just one little thing. So we have seen this vector space earlier. X is any set. Typically, we are interested only when this is a finite set because we are only interested in finite dimensional vector spaces. So F is a field, X is a finite set. Then this is the set of all maps from the set X to the field F. And this has a natural vector space structure where we add two functions pointwise and we scale them pointwise. So just to recall the vector space structure on it. All right. So with that, let us begin. So what is a matrix? Fix a field F and fix two positive integers m and n. Then an m cross n matrix over the field F is somewhat informally it's an m cross n rectangular array with each entry being with each entry coming from F. So it's a somewhat informal definition. An m cross n matrix looks like this. We have m rows, we have n columns, and once you choose a row and a column, you get a cell or an entry, and this guy is an element of the field F. Okay, so there are m times n many entries available, and such a thing we may in short write like this. So even before we go there, when we write A11, what we really mean, what we should be writing is, we should be writing A1, 1. That's what we should write. It looks like A11, but what we mean is A1, 1, but I don't like to write this comma. It becomes too much. So A2, 3 here is A2, 3 and so on. All right, and this whole thing, this whole box can be in short denoted via this notation. You make two rectangular brackets, write the generic entry here, and denote the number of rows and the number of columns. So that's your informal definition of a matrix. This is how we think of a matrix. All right, but here is the formal definition, more formally. An m cross n matrix over F is a function from this set to the field F. So this is the formal expression. What was the problem here? The problem was rectangular array is not a formal mathematical object. Typically we build mathematics with sets and functions and relations as its foundation. Rectangular arrays have not been declared. So you can think of this as a rectangular array. The domain is, you can think of the domain as an m cross n grid, and this is an assignment to every entry, an element of the field F. So this is exactly what we would like to think as a rectangular array. All right, so this is the formal way to define a matrix, but this is how we think of matrices. We don't think of matrices in this fashion, even though both perspectives are useful depending on the situation. Okay, so lastly, as a point of notation, let me write it here. So we write this to denote the set of all the m cross n matrices over the field F. So this is the notation for all m cross n matrices over F. Just a notation. All right. It's unclear what this has to do with linear algebra as of now. And before we connect it with linear maps, we will develop an algebra on matrices first. So we will define various operations on matrices. The first is scaling. So fix a matrix. So we have some field F already fixed, and A is some matrix. So this is of course an element of this set. All right, and fix a scalar. So then we define alpha A as this matrix. We just entry-wise scale the things. Right? Now, this is not really anything new. We haven't defined any new operation because once you think of a matrix as a function from what we said, from 1 to m times 1 to n to the field f. So if you think of A as a function from there to there, this is how we scale functions. We scale functions pointwise, and that's exactly what this is. So just correlate with our usual way of scaling functions, right? So in other words, what we are doing is, if you think of this as just maps, if you think of that just as maps from this set to that, which it is, this is exactly that in the formal picture. This is how we scale an element of this vector space. This you can think, I mean, this we know is a vector space, and this is how we used to scale things in this vector space, right? So I have already kind of spoiled it. This is going to become a vector space, but this is not going to be a new vector space. It is this vector space. We are just beating the details down once again. One interesting thing that will happen here is that we will also be able to multiply things here, which we did not do here. I mean, one can multiply things here, but not in the natural way. I mean, not the first thing that comes to mind is what we will do. It won't be pointwise multiplication. Anyway, we will come to that. So now let's define addition. So the second thing is addition. So this time we have two matrices. So we have two matrices, A and B, both of the same type. So they are in this set. So we define A plus B as the matrix which is obtained by adding entry-wise. So again, this addition is the same as we used to have here. You think of this space as that. This is exactly how we would add in that space. So far nothing new has been done, but here is the new thing. So here we have two matrices. One is in this space, m cross n, the m cross n matrices, and the other is in the n cross k. So m and k are positive integers in that space. And now define the product A times B as this funny thing. So you multiply an m cross n matrix with an n cross k matrix, it becomes an m cross k matrix. And the ijth entry looks like this. It's a very funny looking thing, and there's a good reason why this definition has been given. This is not the natural thing that you will do if you think of this space as that and so on. But there's a reason why we defined it this way. Recall, we never talked about multiplication here. One can come up with an obvious definition that would be pointwise multiplication, but this is not pointwise multiplication. This is far from pointwise multiplication. So we will see why this definition was given. This is sort of a post hoc thing. But anyway, so we have scaling, we have addition, we have multiplication, these three operations. And now with just the scaling and the addition, we have the following observation, that if we have a field f and we have two positive integers m and n, then this set is a vector space under the addition and the scaling operation. Vector space over F. Okay. So again, this is nothing new. Once you think of this as the set of maps from the cross of the first m and the first n integers, this is exactly the vector space structure that we have. So this is nothing new. This is not a new construction. All right. So now for the important part, we will connect this notion of matrices with linear maps. So suppose V and W are vector spaces over a field F, and we have a basis for V and a basis for W. Then for any linear map, so you pick a linear map from V to W, then what we will do is we will take the image of each basis vector here. So say T of Vj, so this is the jth vector in this basis, and this lies in the vector space W, and therefore we can express this uniquely as a linear combination of those people. And let me write that vertically. So let's say that combination is alpha 1j W1 plus dot 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 plus alpha mj Wm. So all we are saying is that this can be written as a linear combination of W1 up to Wm. You will get some scalars. We are just giving them names alpha 1 comma j up to alpha m comma j. So in the usual horizontal way of writing, we would have written this thing. Okay, now with this in mind, we define the matrix of T with respect to the two bases as notationally it is this thing, and its entries are just the alpha ij's. So let me cut the long story short. This is equal to this m cross n matrix. Right? So this is how we define the matrix of a linear map. This is of course sensitive to the choice of the bases. You change the basis, the matrix will change, because the things that you are using to express something as a linear combination is changing. In fact, the vectors that you are feeding in are also changing if you change the elements of the basis B. So this is sensitive to the choice of the bases. And yeah, so to any linear map, you can associate so many numbers. You can associate a rectangular grid. Each of its entry is an element of the base field. So that's the definition, but what is it good for? Before we go there, let us look at a specialized version of the previous definition. Fix a vector space and fix a basis of it. Then, for any endomorphism, we define the matrix of this endomorphism with respect to the chosen basis as notationally it's this, and the definition is borrowing from the previous slide, that thing. So this was defined in the previous slide. We have a linear map from V to V. So here and there we use the same basis, the one chosen, and therefore this is meaningful, and this is what we are defining. So once you have an endomorphism, you need not choose two different bases to define a linear map. You can choose two different bases. If you choose two different bases, V and B prime, then you can form this matrix This you can form, but you may just choose one basis and define this object. And this is what we typically do. We do not typically need two different bases when working with the same vector space, when working with endomorphisms. Okay. So now here is the thing. All these definitions, they interact well with each other. Fix two vector spaces both over the same base field, and fix the bases B for V and C for W. Fix two linear maps S and T both from V to W. Then the matrix of their addition. So you can add two linear maps as we saw. The matrix of their addition with respect to the chosen basis is the addition of the corresponding matrices. So this is the reason why we defined the sum of matrices entry-wise, right? If you define the sum of two matrices entry-wise, then this equation holds true. That is the reason for that definition, even though that's a very natural one, right? So this is the thing. You can verify this, and this is an exercise. Very simple. Similarly for scaling. So we have two vector spaces over the same base field. We have a basis for the first one, a basis for the second one. We have some linear map from the first to the second vector space and fix some arbitrary scalar. Then the matrix of the scaled linear map with respect to the chosen bases is the scaled matrix with respect to the chosen bases. This is again an exercise. Please do not skip these exercises. This will make you comfortable with matrices and generally teach you about linear maps. Finally, we will explain the reason for that funny definition of multiplication of matrices. Fix three vector spaces U, V, and W all over the same base field F. Fix three bases A, B, and C respectively for U, V, and W. And let's say T and S are linear maps. T is from U to V and S is from V to W, so that one can compose the two. You can form this composition U, V, W. This is T, this is S. So this would then become that thing. So this is S composed with T, that thing. So then the matrix of that composite with respect to the correct bases. So this composite is from U to W. So here we have the basis chosen for U and this is the basis chosen for W. So this is the multiplication of the matrices. This is equal to that. Okay. So I hope I am not making a mistake here. Yeah. So let's continue from this place. Right. So now we will finally talk about an isomorphism between the space of linear maps and the space of matrices. Again, this is very, very simple. You have two vector spaces over the same base field and we have chosen bases for each of them. Then we have this map, call it phi, going from all linear maps from V to W to the space of matrices. So here M is the dimension of V and N is the dimension of W, or no, it's the other way. So M is the dimension of W and N is the dimension of V. I mean the correct things basically. Defined as, it takes a linear map to its matrix with respect to the chosen bases. This is a linear isomorphism. So this is again an exercise why this is a linear isomorphism. That's very easy. The philosophical content here is that once you have chosen the bases, chosen a pair of bases, one for v and one for w, you can pass to this more concrete looking space and do your linear algebra here. Philosophically speaking, many times this is more comfortable, but you can pass everything to matrices. And in fact, a lot of people do linear algebra this way. They do linear algebra over matrices and then transfer the results to linear maps. In this lecture series, we are going the other way. We do linear algebra here and then we may deduce results about matrices using our knowledge here, but not necessarily always this would be the case. Sometimes this is more comfortable. Okay, so this is one thing. And lastly, one more definition. Suppose F is a field and we have a linear map from these two coordinate spaces. M and N are positive integers, so we have a linear map from F to the N to F to the M. Then, since here we have a natural choice of bases, the standard bases basically, we may directly say the matrix of T is, when we write this, we mean the matrix of T with respect to the standard basis of the first space and the standard basis of the second space. That's what we mean. Okay, so here we do not, when we do not prescribe any specially chosen bases, then we may just write this and this is what we mean. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.